So for number 8, it says if a cannonball is fired with a velocity of 370 feet per second, it will follow the graph of this function where distances are measured in feet. Part A says plot the graph of the flight of the cannonball. So the window that I used was 4,000 for the X max and 2,000 for the Y max, and the graph looks like this. For part B, it says find the height of the cannonball 3,000 feet downrange. So I just need to plug in the value of 3,000 to get the Y value or the H value, which is the height. So if we just do calc value 3,000, then we should get 896.27 feet. Part C says by looking at the graph of H, determine when dH over dx is positive or negative at 3,000 feet downrange. So they want us to look at that same point that we were at and determine if it's if the rate of change, if dH over dx is positive or negative. Well, since this is decreasing at this point, it's going to be negative. So the function is decreasing. So dH over dx is negative. For part D, it says calculate dH over dx at 3,000 feet downrange and explain what this number means in practical terms. So we can actually use a new function here that we haven't used before, and that's calc dy over dx. So if you go to your calc menu, it's below the intersect command, and it's dy over dx. And then it doesn't really have a command prompt, so if you just show or just type in 3,000 and enter, then it should give you the value. And I'm going to round it to 2 places here, and this is negative 0.40. So again, it doesn't really give you like a x is equal to, you just have to type it in, but you should be able to get the negative 0.40. So what does this mean? This means that when the cannonball travels 1 horizontal foot downrange from 3,000 feet, we expect it to decrease in elevation .40 feet. So that'll be our answer. I do want to talk a little bit about the dy over dx. So, like the slope is always changing in this function. Is always changing. So before in this section we were estimating the rate of change. We were finding like the 2 points and finding the slope between it. So this dy over dx that we're using on the calculator, this is finding the slope at really any specific point. So we found it at like 3,000 was around right there, and we got it to be, so dy over dx was negative 0.40. If I were to type in dy dx negative, let's say 3,500, or sorry, positive 3,500, that's like around here, and this dy over dx is equal to negative 0.63. So the rate of change is bigger and in the negative direction still. So it's actually speeding up as we continue downward. If we were to calculate dy over dx, let's go 3,700, then that would be negative 0.73. If I were to calculate it somewhere over here, let's go 1,500, then this would be 0.30. Notice it's a positive 0.30. And if I were to go, and let's pick 1,800, then dy over dx is equal to 0.16. And that 0.16 is slower than the 0.30 because as it reaches the peak, it's slowing down, and it's going to actually come to a stop at the very top there. So again, your rate of change is always changing. And we were estimating it before by taking 2 points and finding the linear slope between them. But the dy over dx command actually gives you the actual rate of change at each individual point. So it's quite an important application to figure out the actual rate of change at each instant.